Hello, in this video, I'll be discussing on the models of an atom. But before we go on, if you are yet to subscribe to this YouTube channel, please do well to click the subscription button, like this video, and also share it to others that would also benefit from it. So let's get started. So to start with, what is an atom? Now, an atom is simply the smallest part of an element that retains the chemical properties of the element. So in this case now, think of element as the big guy, and then the smallest part of that element that retains all of the chemical properties of that element is what we refer to as atom. So take for example, if you have a large quantity of sugar, now the smallest bit or the smallest size of that sugar that can still be referred to as a sugar and still retain all the chemical properties of a sugar is actually what we refer to as an atom, right? So the first attempt to study into the concept of an atom was actually done by a scientist known as John Dalton in the year 1803. So he was the first person, the first scientist to attempt to study into the concept of an atom. Of course, right before this time, there has been contemplations on atom, even from the time of Democritus, Aristotle. But the first attempt to study into the concept of an atom was done by John Dalton in the year 1803. And in his attempt, he described an atom as an indivisible solid mass. Now, what this means is that what John Dalton explained that an atom cannot be further divided into smaller parts. That's what he meant by indivisible solid mass. And then he also proposed atomic theories that explained the conservation of matter. Atoms can neither be created nor destroyed. Atoms of the same element are alike in every aspect, different from atoms of other elements and others. But unfortunately, there were some limitations to the study of atom by John Dalton. Now, some of these limitations was that he could not account for the following. He could not account, number one, for the concept of isotopes. Now, what are isotopes? Isotopes are simply atoms of the same element that have the same atomic number but different mass number. So the atomic theories of John Dalton could not account for the concept of isotopes. Also, his theory could not account for the concept of subatomic particles because he explained that matter, that atom rather, is the smallest part of an element and it is indivisible. So he could not account for the existence of the subatomic particles as we will later get to know in this study. And third was that he could not account for the electrical nature of the atom. The electrical nature of the atom. So these were the major limitations of the study of an atom by John Dalton. So now let's move proper to the models of an atom. Now in this video, I'll be talking about three models of an atom. The first model is the plum pudding model. The second model is the planetary model. The third model is the quantized model. And then the fourth is the quantum model. So let's quickly discuss these various models of an atom and identify the things that we need to take note of for each of these models. And let's start from the plum pudding model. Now, in the plum pudding model was proposed by a scientist known as J.J. Thomson in the year 1897. He proposed the plum pudding model. And what do you mean by the plum pudding model? He proposed that an atom is a solid mass that consists of positive and negative electrons that are randomly dispersed inside it, something like this. So this is what we refer to as the plum pudding model. It proposed that uh, uh, electrons and protons are evenly distributed. Positive ions, negative ions are dispersed inside a solid mass, and that's the plum pudding model. Also, it was responsible for the cathode ray tube experiments. So, in the cathode ray tube experiment, J.J. Thomson discovered the electrons. He discovered the electrons, which are the negative ions or negative subatomic particles of an atom. I was also able to determine the charge to mass ratio of an electron, which he determined to be 1.76 times 10 raised to power 8 coulomb per gram. So I was able to determine the charge to mass ratio of an electron as 1.76 times 10 raised to power 8 coulomb per gram. But there were also limitations to the plum pudding model as proposed by J.J. Thomson. Now, let's discuss about these limitations. What were the limitations to the plum pudding model as proposed by J.J. Thomson? And this model could not account for, number one, it could not account for atomic stability. Number two, it could not account for the nuclear structure. Because if you look at the plum pudding model now, as proposed by J.J. Thomson, he was unable to account for the existence of a nucleus, as we will later find out in this course. So, because of that, there was no explanation to the nuclear structure of an atom. And also, he could not give explanation to the alpha particle scattering, which we will also later discuss in the course of this course. So these, among others, were the limitations of the plum pudding model by J.J. Thomson. Now let's move quickly to the second model of an atom, which I called the planetary model. Now this planetary model was proposed by a scientist known as Ernest Rutherford when he performed an experiment which was known as the gold foil experiment. The gold foil experiment. Now, another name for the gold foil experiment is the alpha scattering experiment, which could not be explained by the plumb pudding model of J.J. Thomson. The alpha scattering experiment. So Ernest Rutherford performed this experiment in the year 1911, and from this experiment he was able to bring out the planetary model of an atom. Now, how does the planetary model of an atom works? Now, it proposes that there is a central nucleus, and then this nucleus now is surrounded by orbits, just like this. And then on this orbit now, we have the electrons. And these electrons are said to revolve around the nucleus in their orbit. Now, what caused this? Now, in the gold foil experiment that was performed by Ernest Rutherford, when rays were made to pass through the gold foil, now he discovered that a lot of the rays passed through the gold foil, and then some of these rays were deflected, and then we found a very few amount, a very minute amount of this ray that bounced back. So he described it more like a gun that was being shot at a sheet of paper, and then the bullet now bounced back on hitting the paper, which is practically impossible in reality. So this is what made Ernest Rutherford now to discover that the atom, contrary to what was explained by J.J. Thomson, had a central mass, which is called the nucleus, which is a tiny mass found at the center of the atom. And it is this nucleus now that actually determines the mass of the atom and also contain the positive charges. So it's a positively charged nucleus. And that is what we have here. The positively charged nucleus. And then we have the orbits, and then the electrons, which revolves around this central nucleus on their orbits. So that is simply the planetary model. You can see it looks like the planetary system, various planets revolving around the sun. That is what it is referred to as the planetary model. But then this model of an atom also have a number of uh, limitations. Now let's discuss about these limitations. The limitations of the planetary model of an atom as described by Ernest Rutherford. Now the limitations was that the model could not explain the following. This model could not explain the following. Number one, it could not explain the concept of atomic stability. Now, let me explain more on this atomic stability. Now, if you look at this model proposed by Ernest Rutherford, same with the model that was earlier proposed by J.J. Thomson, you understand in mechanics that unlike charges attract while like charges repel. Now, in this planetary model as proposed by Ernest Rutherford, you would see that the nucleus is said to be positively charged, while the electrons on the orbit are negatively charged, which means they would attract because unlike charges attract. Now, if the electrons are being attracted to the positively charged nucleus, then at the long run, the whole atom will collapse, right? So that does not give a proper explanation to atomic stability. Also, this planetary model does not also explain the line spectra of elements. Now, what do we mean by line spectra of elements? Now, it was observed that when elements are subjected to great heat, which increases their energy content, they emit line spectra, which shows uh, uh, change in the energy content of the atoms of that element. But this model, as proposed by Ernest Rutherford, could not give a proper explanation to the emission of line spectra by elements. So that would take us to the third model of an atom, which I called the quantized model. Now, the quantized model was proposed by a scientist known as Niels Bohr in the year 1913. And in this model, he actually introduced the concept of energy levels. He introduced the concept of energy levels, where we have energy levels noted by N equal to 1, 2, 3, 4, and so on. So which means the orbits now on which the electrons revolve around the nucleus are actually energy levels, as opposed to the planetary model by Ernest Rutherford. So the following are the postulates of the quantized model as proposed by Niels Bohr. Now, number one, he explains that electrons move in a fixed circular orbit. Number two, he postulated that orbits are indefinite energy levels. And then third, he explained that energy is released or absorbed only when electrons transitions from one energy level to another. So these three postulates is what properly explains the Niels Bohr model of an atom. And then we have it's just like this. Of course, the nucleus, and then around this nucleus now, we have the orbits at energy levels. And that energy level means now that n equal to 1, n equal to 2, n equal to 3, and so on and so forth. Various energy levels on which we have the electrons that are revolving around the nucleus. And we see that these electrons now move in fixed circular orbits, and these fixed circular orbits now are indefinite energy levels. So this accounts for the transition of an electron from one energy level to another, which can cause energy to be either released or absorbed, which properly explains the emission of line spectra when elements are heated. So this now is like an advancement over the planetary model as proposed by Ernest Rutherford. So this better explains atomic stability. Explains atomic stability from the understanding of the fact that the electrons are in energy levels. So the inner electrons shields the outer electrons from the effect of the positively charged nucleus. So this ensures the stability of the atom. And like I said earlier, it also explains the emission of line spectra. But unfortunately, there are also some few limitations to this model. Now, what are these limitations? Now, number one is that it works only for hydrogen and hydrogen like atoms. The Neil-Bohr model can only work for hydrogen and hydrogen like atoms, which means it does not work for what? For multi electron atoms. Once an atom has more than one electron, the Neil-Bohr model cannot give an explanation to the emission of line spectra from multi-electron atoms. Now, another limitation with the Neil-Bohr model is it cannot explain the Zeeman effect and Stark effect. Now, these two phenomena cannot be explained by the Neil-Bohr model. And then lastly, the Neil-Bohr model of an atom cannot explain the wave nature of electrons, cannot explain the wave nature of electrons. So all of these limitations now is what brought about the proposal of a much more advanced model of an atom, which we refer to as the quantum model of an atom. And this now is a modern model of an atom. Now, because of our time, I might not be able to talk much on this quantum model. I'll just mention a few of the scientists that contributed to the quantum model of an atom. It was not proposed by a single scientist. We have scientists like Heisenberg. Heisenberg proposed what we call the uncertainty principle, which is a principle that explains to us that the exact position of an atom or of an electron rather in an atom cannot be determined. The exact position. So what can be determined is the average position. That is what Heisenberg told us. Then we also have scientists like de Broglie. Now de Broglie simply explained the wave particle nature of an atom. We call it wave particle paradox. That is what was explained by de Broglie, the wave particle paradox, that explains that electrons can behave both as an electron, rather, electrons can behave both as a wave and as a particle. I won't be able to talk more on that. We have other scientists like Schrodinger and others. But before I end this video, I would also want to make mention of some other scientists that even though they didn't propose a model of an atom, but were also very instrumental in the overall knowledge that we have now concerning the atom. Now, who are these other scientists? Let's mention a few of them as we bring this video to a wrap. And one of them is James Chadwick. James Chadwick discovered the neutron. Discovered the neutron in the year 1932. You have scientists like Robert A. Millikan. And Robert A. Millikan performed the oil drop experiment where he discovered the charge of an electron. So he determined the charge of an electron to be minus 1.6 times 10 raised to power minus 19 coulomb. So, and you remember that earlier, J.J. Thomson determined the charge to mass ratio. So if you do your mathematics now, from here now, you're able to determine the mass of an electron. By the time you divide the charge of an electron by the charge to mass ratio of an electron, you discover that the mass of an electron is equal to 9.1 times 10 raised to power minus 28 gram. That's the value of the mass of an electron. And lastly, let me mention Eugen Goldstein. We actually have a lot of scientists. We have likes of William Crookes, who developed the cathode ray tube. We have likes of Becquerel, who discovered radioactivity. We have Roentgen, who discovered X-rays, just a number of them. Well, Eugen Goldstein, lastly, in the year 1886, discovered the proton. Discovered the proton, even though as at that time he didn't call it a proton, he called them canal rays, or anode rays. But these were actually what turned out later to be the proton, right? So in summary now, we discovered that an atom now is made up of 3 subatomic particles, right? From all that I've explained so far, 3 subatomic particles. Number 1, we have the neutron, which is neutral. We have the proton, which is positive. And the neutron and proton now are both found in the what? In the nucleus of the atom. And then lastly, we have the electrons, which are negatively charged. And the electrons now are found on the orbits, moving around the nucleus. Of course, over time, we discovered that they were not actually orbits, but they were orbitals. And this is why I'll be stopping this video because of our time. But I want to believe you've learned one thing or the other in the course of this video. And if you are yet to subscribe to this channel, please do well to subscribe. Share this video with those that can benefit from it. Click the notification bell to receive notifications whenever I drop a new video. So till we meet in the next video, do take care of yourself. Bye.